today's problem. A charge of Q equals 4 times -6 coulombs experiences a force of 0.2 newtons pointing eastward due to a large uniform electric field. A loop with a radius 0.50 meters, so this is a circular loop, forms an area vector 60 degrees with the direction of the electric field. And the question is asking us to find the electric flux through the loop. So let's draw a diagram for this. Here we have our charge with the force 0.12 newtons pointing eastward, and here we have our uniform electric field that the charge is placed inside, and our circular loop that is near the charge, where its area vector forms a 60-degree angle with the electric field. So to test the electric field's magnitude, we place a charge inside it. So we can use this equation and see what electric field magnitude we get. And we're going to get an electric field value of 30,000 Newton over coulombs. So now we have to find the area of the circular loop, which we have to use in an equation later. So the area of this circular loop is going to be A equals pi, or squared. So this is going to be A equals pi 0.50 squared. And we're going to get 0.785 meters squared as our area of the circular loop. So now putting it all together, to find the electric flux passing through the circular loop, we have to use the equation EA times cosine of theta, where theta is the angle of the area vector relative to the electric field direction. So we can plug in our electric field value, which was 30,000. We plug in our area value, which was 0.785, and we can plug in our angle, so cosine of 60. And we're going to get our final answer as the total electric field passing through the circular loop being 11,775 Newton times meter squared over coulomb. And that's our answer. So to explain this problem more conceptually, we have a strong electric field that is already in this space, and we're just placing a charge inside it. And this creates a force that pushes it eastward, or the direction of the electric field, where we can find the electric field magnitude because we have a charge, because this equation says that the electric field equals the charge over the force. So we can just put the charge amount over the force, and then we can find the electric field just by placing the charge in the electric field. So the area vector, just imagine we have a flat surface, and let's say this pen is on the flat surface. The area vector is pretty much what direction this pen is pointing to the ceiling. And since this loop is tilted, that means its area vector is going to be pointing slightly upwards to the electric field, making it a 60-degree angle. Alright, next problem. Find the magnitude of the electric field and the electric flux passing through the slanted face of the prism. And this is our prism. So here we have an electric field, and we have a charge that is inside the electric field with 5 times 10 to the negative 6 coulombs, and the electrostatic force pointing eastward. We have a prism with a height of 0.60 meters, and the width of the face is 2 meters, and we have to find the electric flux passing through the slanted face, so this side right here. So first, to find the magnitude of the electric field, we're going to use this equation E equals force over charge. So if you're plugging our numbers, the force is 0.20 newtons, and the charge is 5 times 10 to the negative 6 coulombs, giving us an electric field value of 3,000 Newton over coulombs. And same thing before, we have to find the area that the electric field is passing through. But this question is asking us the electric flux passing through the slanted face, so not this entire prism, just this face right here. So the area of that is going to be the length times the width. So in this diagram, it shows that the width is 2 meters, so we can just put that in. To find the length here, you can just use some trigonometry to find that the cosecant of this angle theta here, 30, is going to equal the length over the opposite, 0.60 meters. So we're just going to multiply 0.60 to both sides, and we're going to get our length as 1.2 meters, meaning that our area is going to be 1.2 meters times 2 meters, which is going to be 2.4 meters squared, and that's our area. Finally, putting it all together to find the electric flux, it's going to be the same equation, EA cosine of theta, but theta here is actually not going to be this angle 30, but it's going to be the angle of the area vector, which is going to be 60 because 90 minus 30 is 60. And that's because the area vector must point perfectly perpendicularly out of the ramp. Plugging in our numbers, our electric field is 40,000 Newton over coulombs, our area is 2.4, and our angle is going to be 60, giving our answer to be 48,000 Newton times meters squared over coulomb. So here we have a setup here with our charge at 5 times 10 to the negative 6 coulombs, and applied force of 0.20 newtons, and our rectangular prism here. And let's just click next to see the electric field lines, the surface, the area vector at 60 degrees, and we can see that the electric flux passing through the surface here is going to be 4.8 times 10 to the 4 newton meters squared over coulomb, which is 48,000 as we predicted. And yeah, that's the video. Thank you for watching.